Hi everyone, welcome to the JGM YouTube channel. So this week we'll just be doing a sort of short video on power of a point, which is a nice little trick you can use on ratios of line segments involving circles, and the theorems can really help in competition math. So the length of an arc is a measurement similar to how one would measure how long a line is. So an easy way to find the length of an arc is to just find how long it is based on the percentage of the diameter. And this is just based on the circumference, right? So if we have a circle O, if the angle x, let's say x and y are points on the circle. So if the angle XOY is equal to 60, find the length of arc xy if OX is equal to 8. And at this point, I should mention the terms major and minor arc. So if we have 2 points on a circle, we're going to have a major arc and a minor arc, right? Because there's 2 arcs we can form. We can form one arc that comprises just a small part of the circle, or another arc that comprises most of the circle. And for all intents and purposes, if we say arc, we are implied to mean the minor arc, unless explicitly stated that it is the major arc. So if we say arc, that just means minor arc. So the major arc in this case would have an angle of 300, right? Because that's just the other angle, right? Because 360 is the complete circle. So we know that 60 degrees is 1/6 of 360 degrees, so xy, the minor arc, should be 1/6 of the circumference. And so in this case, how we would find the length of the arc is, since we know that OX is equal to 8, that's the radius, so the diameter is going to be 16, so the circumference must be 16 pi, so our answer would just be 16 pi divided by 6, right? So that would be 8/3 pi. So that's how we find the length of an arc. And in this case, we can also say that the arc xy is 60 degrees, so that's the measure of the arc. And we can measure arcs in degrees just like how we measure angles. So what if instead of measuring from the center, we are measuring from another point on the circle? And this is where something called the inscribed angle comes into play. If we have 3 points ABC on circle O, angle ABC is going to be 1/2 of angle AOC. Okay, so an inscribed angle has half the measure of the arc it includes or subtends. So just for a better visualization of this, if we have some circle like so, this would, yeah, this is much better. I don't know why. But anyway, so let's say we have some circle here, and we have 2 points, right? Let's say this is A, and this is B, okay? And then this is the center O. So center would look something like this. So this is our center O, okay? And basically, if this angle is, let's say this angle is theta, this is how we denote angles. This angle is theta. If the angle AOB is equal to theta, right? If the measure of this angle equals theta, then the measure of the arc AB is also going to be equal to theta, okay? So, but the interesting thing here is that if we have some angle like this with another point on the circle, let's call this x1, okay, x sub 1. Angle, the measure of A x sub 1b is going to be equal to 1/2 of theta. All right, and this goes for any point on the circle. I could have this point, right? Well, that's not really on like that. This is also the same. These two are the exact same measure. Could have this. We could have this right over here. All of these are the same angle. These are all the same angle measure over here. Alright? So for x3, x4, x5, these are all really the same. So this is all theta divided by 2. So this is still equal to m a x2b equals m a x3b, and so on, right? These are all the same. So that's what the inscribed angle theorem is. It's just 1/2 of the angle it includes, right, or subtends. So there are some special lines involving circles called tangents, secants, and chords. Tangents are lines that touch the circle at exactly a single point. So they don't really intersect with the circle, they touch the circle, right? Just touch one point. Secants touch the circle at 2 points, so they just kind of go through the circle. And chords are line segments that start at one point on the circumference of the circle and end on another point on the circumference. So to give you a better visual, let's have another circle here. And our tangent here would be, it would look something like, we want something that intersects the circle at one point. So it would look something like this, right? So it intersects at exactly this point. Okay, and this is our tangent. Let's call it L1. That's our first line. And this is our tangent. You can see it only intersects at one point. It doesn't go through the circle at any point. It just intersects at one point, just touches it. A secant is a little bit different. A secant is going to pass through the circle. So we can call this L2. This is a secant. L2 is a secant. So it's going to touch the circle at 2 points. It's going to intersect at this point and this point. So this is what a secant looks like. It just goes through the circle. And a chord is going to look something like this, where it's just a line segment that starts at one point on the circle and it ends at another point on the circle. So both of its endpoints are on the circle. And if you see this secant right here, this secant actually contains a chord. So the part of the secant that is actually inside of the circle, that is a chord as well. So these are special lines and line segments involving circles, and they will be very useful to us just very shortly. So a tangent to a circle at a point P is always perpendicular to the radius of the circle at that point. So this is always true, always perpendicular to the radius at that point. And another thing, two tangent lines from a single point are going to be equal in length. And you might be wondering, what does that mean? Well, here, let me just draw another circle. Let me draw two tangent lines to this circle. So let's have one tangent line. Well, that doesn't really look like a tangent. More like that, yeah. And then this. Sorry, just having a bit of an issue with these here. Okay, I'm going to use something called the big point theorem here, where it doesn't really intersect, but I'm just going to pretend it does. I'm going to draw a big point. Just pretend it intersects there, alright? Pretend it does. And, so we can call this A, this is N, this is M. So one nice thing is that the point that the tangents are, so AN and ANM, these are actually equal to each other, okay? So the tangent line segments are always equal from that point of intersection. So two tangents from a single point, the distance between that point and when they intersect with the circle, these are going to be equal. So AN is equal to AM. Those lengths are equal to each other. And and these are also perpendicular. So yeah. So this brings us to our first power of a point theorem, which is the tangent second theorem. So given some point P and a tangent AP, and a line BCP that intersects the circle at B and C shown below. So let me just give you a bit of a better diagram for that. So we have some tangent like so, and this is going to be AP, okay? And it only intersects, sorry, this is going to be AP. They're all going to come from P, okay? This is very important that the tangent and the second both start on the same point. Although the thing is they're going to intersect, right? They're two different lines, so of course they're going to intersect. And that's going to be our point. So let's say their point of intersection is P, right? And the second has B and C here. So our first power of a point theorem states that PA squared is equal to PB times PC. And notice, very common mistake. Some people think that it's PB times BC. It's not, okay? So remember, it's not PB times BC is equal to PA squared, okay? This is not correct. This is wrong. This is a very common mistake. Don't do this. Do not do this, okay? It's PB times PC. So it's the outer part. Here's a way to remember. Outer part multiplied by the whole part. Okay, so just outer times whole. Alright? And for PA, this is just really simple. It's just this part, right? The part between intersection squared. So that's simpler. And yeah, this is our tangent second theorem. So it's the first of our three power of a point theorems. We also have the second theorem. So given some point P and a second ABP and a second CDP, the power of a point second theorem states that PA times PB is equal to PC times PD. So let's see. So very similar diagram we have here, right? This is P, and we have two seconds. We have this, and we have this. So very similar to what we just wrote. We have PA times PB is equal to PC times PD. And yeah, that's basically what it is. It's just, again, outer times whole is equal to outer times whole is one way you can remember it. And finally, we have the chord theorem. So this part of power of a point states that when two chords A, B, and C, D of a circle intersect each other at a point X like so, then the product of the two parts of one chord is equal to the product of the two parts of the other. So AX times XB equals CX times XD. So if we just sort of write that down here, or that's a circle, make a better circle. So if we have two chords kind of here, you know, any two chords, any two intersecting chords. Let's have A, B, and C, D intersecting at some point X. Okay, this is the point of intersection X. Then AX times XB is going to be equal to CX times XD. So the product of the two parts of one chord, right, the part before and the part after the intersection, is equal to the product of the two parts of the other chord. So this before and after intersection. And this works for any really chords that intersect at that point. So yeah. So those are our 3 power of a point theorems. So here are some introductory power of a point problems. So I'm going to give you 5 seconds to pause the video and find x in the first 2 diagrams. The third one is kind of broken, so... So, okay, let's just try to do these questions. So, our first question is we have a circle, like so, and we have 2 seconds. So, A, B, C, D, E. And we're given that BC is equal to 5, AB is equal to 3, and that DE is equal to 10. It wants us to find x, which is the length of AD. So what we know is that AB, right, times AC, remember, it's always AB times AC. It's not AB times BC. That is a common mistake. Do not do that. It's always the outer part times the whole thing, right, is equal to AD times AE. And this is going to end up being, if we just plug everything in, we're going to have 3 times 5 plus 3 is equal to 8. It's going to equal x, right, times x plus 10. So we're going to end up with 24 is equal to x squared plus 10x. And actually at this point, you might not even have to find what x is using a quadratic equation. You can just see, wait a minute, if x equals 2 just works, right? Because 2 times 12 equals 24. But let's just solve it with the quadratic method, because we did that last week, right? And it's going to be a good refresher. So x squared plus 10x minus 24 equals 0. And if we just factor this, remember, we're looking for 2 things that multiply to negative 24 and add to negative 10, right? So that's going to be negative 2 and 12, right? So we can just turn this into x minus 2, x plus 12. And of course, now we have our solutions. Either x is equal to 2 or x is equal to negative 12. But this is not happening, right? You can't have a negative line. This is an extraneous solution, so this is our only solution here. X equals 2. And let's also do our next problem. So this is a chord theorem question, as you might have observed quite easily. So we have our 2 chords here, B, E, D, C. And then we have our point of intersection here, A. And we're given that BA equals 1, AC is equal to 4, AE equals 6, and then we're trying to find x. So this one's, I think, a bit more straightforward. You're going to have AB, right, times AC equals AD times AE, right? So this is going to be equal to 1 times 4 equals 4. And then this is going to be x times 6, right? So this is 6x. So we have 6x is equal to 4. And of course, x is just equal to 4 over 6, which is equal to 2 over 3. Simple. So this is our answer. So we can also solve some more intermediate problems. So a square of sine length 10 has a circle inscribed in it. Let M be the midpoint of AB. find the length of the portion of the segment MC that lies outside the circle. So I'll give you 5 seconds to think about this one and pause the video. Okay, so we have some square of side length 10, so and it's got some circle inscribed in it, so it's going to be A, B, C, D. Should have specified that M is here, right? And it's the midpoint of AB. So we know that this is going to be 5 and 5, right? And we want to find the length of the portion of the segment MC that lies outside the circle. So we have a circle that is going to be inscribed in here. And that circle just made me realize how bad my square was, but okay. So we have MC, and we want to find the length of this portion right here, this part. How long is this portion that is outside of the circle? So let's call this point X, right? Okay. So first we want to find what is MC as a whole. Well, that's easy. We have MB, right? And we have BC and MC. That forms a right triangle, right? Because squares just form right angles. And so MC is just going to equal the square root, right, of 5 squared, which is 25, plus 100 squared, which 10 squared, which is 100. So this equals square root 125. And you're going to find that this is going to be equal to 5 times square root 5, if you just simplify it a little bit. Because this is just equal to 5 times 25, right? Okay, so MC is equal to 5 square root 5. Great, what next? Well, we can use power of a point. Remember that XC, right, times MC, right, outer multiplied by whole, is going to be equal to, by the tangent second theorem, whatever this tangent's going to be, right, over here. And we know that this is going to be half of the length. So this tangent right here, that's going to be 5. And this is equal to tangent squared. So this is 5 squared equals 25. And we know that MC is equal to 5 squared root 5, so we can just plug that in. So CX, what we want, multiplied by 5 squared root 5 is equal to 25. So this is just equal to 25 divided by 5 squared root 5, so that's going to equal 5 over square root 5 is equal to square root 5. So our conclusion is that CX is equal to square root of 5. So that's pretty much all there is on power of a point. Thank you all for watching the video, and I'll see you next time.